Okay, it's recording. Share the screen again. I'm gonna actually turn off the computer sound because we shouldn't need it now. All right. So, okay, we have, let me actually move this off of my writing space though. We have our Dirac delta function that we've employed, and we've employed it in such a way. Uh-oh, now my little device is being messy. Sorry. Back and forth, back and forth. My Wacom stopped working. Hang on a sec. Okay, there we go. All right. Now we should be um, sort of ready to go. Okay. So we've employed our Dirac delta in such a way that we can write something of this form. Integral from minus infinity to infinity of the complex conjugate of one of our two momentum states times the other momentum state. Remember that we had P2 and P1 here to represent these two momentous states, should equal the Dirac delta function difference between state 2 and state 1. Okay. Now our normalized states have this form phi p of x is 1 over square root of 2 pi h bar e to the I px over h bar. So this inner product is, I should have made note here. This is, of course, an inner product, right? We're doing the same math that we did before for inner products with position states for any kind of continuous state like this. So this is an inner product that we're taking. So we have this term and we have this term again. So this part just is 1 over 2 pi h bar. And then our functions end up being e to the I p prime minus p double prime, or p1 minus p2 x over h bar dx. And that, of course, is this Dirac function. Okay. Now let's look at dimensions. Left-hand side of this. So left-hand side, these guys, has dimension of essentially x over h bar. Okay, so it basically has dimension length h bar. And remember that h bar is what? What is it that h bar has dimension of?
A circle?
No, it has like dimension. It has units attached to it. Does units have dimension?
Uh-oh.
Okay, so the units that go with h bar are joule dot seconds. So what is that units of? Anybody?
Do you mean like joule hertz or like what are you or
What kind of dimension is this? What kind of quantity? These are units.
mhm.
Dimension would be like length.
Oh,
Kilogram meter squared over seconds.
Okay, those are still units though. We're looking for like length or
Is it
speed or
power?
energy or power or momentum, or it's not power though.
Oh,
Good guess. Power would be joules per second. All right.
um
So what did we
oh
first
yes.
use H bar for in this course? We used it for spin. Remember this? Our spin could either be plus or minus H bar over 2. So what was spin? What kind of thing is spin?
It's angular momentum.
It's angular momentum. This is intrinsic angular momentum. So H bar is the only thing with units in here, is the only thing with dimension, therefore must be an angular momentum. So this is angular momentum. All right, so we have length over angular momentum is our dimensional analysis here. And that's dimension wise 1 over plain old linear momentum, which I'm just going to write momentum here. Linear afterwards. Okay. So since P double prime and P prime are both linear momenta in their own rights, the implication is that this Dirac delta function, the right hand of this entire thing, right hand side, this and this have to have the same units as each other. That's just basic dimensional analysis.
Mhm.
So that means that somehow dimension of this Dirac function is 1 over dimension of P prime minus, or P double prime minus P prime. So our implication is that we have a new difference between the Dirac delta and the Kronecker delta. The Kronecker delta tended to give us a value of 1 or 0 and tended to be more or less dimensionless. Dirac delta has dimension to it, and it's the reciprocal of whatever the dimension is of the thing in the argument. Okay. So we'll set that aside for now. We left off last time having talked about orthonormality, and this was kind of the conclusion to that. We also have completeness. So completeness says, if I sum up all of my states for discrete states, whoops, I've kind of mislabeled this though. I should get
One.
unity, 1, exactly. And so for the continuous states, so a continuous state should look like an integral from minus infinity to infinity of, again, whatever our states happen to be. We could call it P sub n states. Not really P sub n states, just P states. dp. And this should also give me unity. All right. And so now we say, okay, let's try this by doing this, but inserting it into the Dirac expression for wave function. A Dirac expression for wave function, recall, is that the wave function psi of x should look like this inner product between x and psi. Okay, and the way that that looks is psi of x is equal to, therefore, x integral from minus infinity to infinity e's dp. Okay. Now, this statement just is saying all I'm doing is taking this term right here and dropping it between these two. Is it valid to do that? Yes, because this is just the one. And if I have one, it's a really bad one. I have one, or identity or unity, operating on psi like this, then I should just get psi back. So if this right here is true, then this right here must also be true. All right. So now we take these two things and we take these two things and we distribute them. And so what we end up getting is psi of x from minus infinity to infinity of x and p. So that's our first one here. And then p and psi dp. Okay. So what are these terms each? Well, oops. This one right here, the x and p term, this just is your integrand above in the projection of momentum eigenstate p into the position basis. So all we're doing is just projecting, therefore, our momentum states, our eigenstates, into our position bases. Okay, so in some sense, this is kind of akin to getting one of these guys for your momentum eigenstate. Okay, or getting this set of these to make that momentum eigenstate work out. The other term, E and psi, that one is simply the projection of your general state onto a given momentum base.
Dr. Sanders, when you say projection, it makes me think it's a dot product. Is that reasonable?
Yeah, yeah. It's an inner product. I mean, we've been
Mhm.
calling these things inner products all along, and I think in quantum one, I stated that dot product is a type of inner product. So is it correct to say that this is a dot product? No, but it's correct to say that both this and dot products belong to the same general type of thing, which is inner products
Right.
in general. And so we call this inner product, but dot products are a sort of inner product. So they'll have sort of the same result, but in um, spins and whatnot, we would do stuff like this, and our result is some scalar. But this thing right here is really represented by the matrix 1, 0. This right here is represented by the matrix 0, 1.
So
And it is also fair to say that you could represent a plane vector. Like, let's say that you have a position vector S, which is given by X I hat plus Y J hat plus Z K hat. You could, in some sense, represent this as a vector. So we could say like S is represented or representable by, let's say, X, Y, Z. Where all of this breaks down, though, is if I have S and then I want to dot it with, say, velocity. I just want to take the dot product. We know how to do that operation. So I'd end up with X times V1, Y. Somehow I put a Y hat. This is Y J hat. I'd end up with X V1 plus Y V2 plus Z V3. But trying to put it into a form here that works out may or may not quite work out, because if this is how I represent a vector, then this is how I'd have to represent this other vector. And you know that if I take these products, this times this, I'm not going to get something very useful.
mhm.
I have to somehow convert this over to a row vector in order to do it in sort of matrix notation. But
Right.
other than that, like, in some sense, that's kind of I don't know really how to describe it, kind of a math quibble, if you will. It's like we know how to do all of these operations. None of them are difficult. It's just a question of maybe like technical language, or how pedantic do you want to be about, is
Mm,
this and this really the same thing? So as an analogy, dot product works very well.
okay.
And in fact, we used that in the quantum one class as an analogy.
So,
Mm,
one thing that's highlighted to me, I think, is I'm starting to understand with spins in particular that it's a two-sided dimensional space within a single element of three-dimensional space. Is that right?
yeah. Yeah. So spin, it gets complicated because you have, let's say, three different axes along which you could measure spin that are
Yep.
normal to each other. And you can only measure along one of those axes at a time. So you've got your three dimensions, and then for each dimension, there's two possible values for a spin half system.
Yeah.
You want to spin one system, now you've got three possible values. You want to spin 5 half systems. You now have 7 possible values, and so on. No,
Yeah.
6 possible values. Sorry. Okay. So, let's see, I lost my train of thought here. We kind of need to make another distinction, I guess, while we're on the topic of making distinctions between things. So we have psi of x. We know that we can write that as x and psi. So this is kind of your Dirac expression for this wave function. Okay. Does it follow? So this is true, Dirac expression. So does it follow that this right here is psi of p? Put differently, is this and this really the same function but with different arguments? Okay. Are these really the same function? We've done the same operation, but we just get different arguments. And the answer is no, they're not. They actually are kind of different mathematical functions entirely. So x psi and p psi are mathematically different functions. And so to make this distinction, we're going to do something notationally, and I'll do that in a minute. In answer to this question, no, this is not true. Maybe I should put like a red to more fun style. Eh. Winner. Oops. There's the ding. You probably didn't pick it up on yours though, because I turned computer sounds off for you guys. I got an error ding. um, so to do this, um, I was going to have a sneeze and then it just decided not to. To do this, McIntyre does the following. So I'm going to write McIntyre and then I'm going to write my suggestion because I wanted to make a slight departure just because I think mine will work nicer. McIntyre says this. He says, let's say that this right here can represent psi of x. And let's let this right here represent phi of p. Okay. I suggest maybe, and this notation's fine, but just my own kind of personal ease of following what's going on, we could instead use this set of notations. So McIntyre's, uses fewer characters, but in using fewer characters, you kind of lose track of what's going on. Essentially, his both of them. They're just trying to represent the state psi. But we're doing this in different bases. So in his case, he said, okay, to represent psi in the p basis, we will actually just call it phi of p, capital phi. And what I've said is, no, let's instead say that we are now representing it in momentum space, as this function here would suggest, but also that we're doing it with momentum representation. So in my notation, that would mean psi x of p would be, you have some state and it's in the x basis, but it's represented in momentum space. Okay, so this right here is basis, this right here is space. Okay. So how do we get from one to the other? Whether you prefer the McIntyre notation or my notation. How do you get from, say, this to this, whoops, or vice versa?
The
And the
uncertainty
answer
principle.
is, what's that?
The uncertainty principle.
No, no, different principle that we need. Use psi of x. This is really going the other way, but it's okay. We can go either direction we need to. Psi of x is from minus infinity to infinity. Remember that these right here, your base states. These right here is the state that you're actually in, and represented in P and in P space. So these right here are, you're representing them with P as your basis, but you're going in X space. These right here are basis states. Okay. But this right here, this function that I've just done, let's just highlight it. This is actually just the Fourier transform. Albeit applied to space rather than to time. You know, usually when we say, okay, Fourier transform is, and you do an integral e to the I omega t dt, or d omega, depending on which way you want to go. Here, this right here becomes integral from, let's go ahead and put our little, I'm going to put the amplitude out here. 1 over square root 2 pi h bar, since that doesn't really affect the integral itself. And this ends up being your function that you're trying to transform. And remember what these right here are. They are this times e to the I p x over h bar. But this has the exact same form. You know, if you think of this as like being f of t in some sense, this has the same form as e to the I omega t. Okay, over something, but over something is, you know, if you have e to the I px over h bar, this is the same as e to the I px over e to the h bar, and this is constant, so you can also pull it out if you'd like. So this I px dp is like an I omega t dt it is a Fourier transform. You just replace time and frequency with position and momentum. And if you want to go the other way around, looks like this. And basically you would do your psi sub x of x and e to the negative I px over h bar dx. Again, this would be sort of like the akin to an inverse Fourier transform. It undoes the Fourier transform. Okay. And the conclusion to this, and I guess we can just stop with that as our note. Quantum mechanical superpositions behave in like manner to classical wave superpositions. Okay. So in both cases, Fourier transform is going to represent a superposition of sinusoidal waves into a wave packet. And I think what we'll do is next time I have a set of notes that I call my addendum to this, which is discrete superposition with wave packets. And I don't recall if McIntyre really goes into this very much. I mean, he does, but I kind of did it my own. He does it, I think, with 2 states or 3 states, and then I have it for more states. And so we'll pick up with discrete superpositions, which is wave packets and uncertainty, and that is section 6.2 to 6.3. So that's where we'll pick up next time. All right.